Hi everyone. In the previous lectures on the operational amplifiers, we discussed various applications of operational amplifiers where we used negative feedback to realize constant gain and different mathematical functions, mathematical operations. Now, in this lecture, we will look at another interesting application of an operational amplifier where we will actually be using this operational amplifier on intentionally in positive feedback. Okay, and one such application, that application is actually, in fact we'll talk in greater depth about this in this lecture. It's a sine wave to a square wave converter. Where do we need sine wave to square wave converters? One example is a function generator. A function generator is a device which can generate a host of periodic waveforms. It can generate a periodic sine wave, it can generate a periodic square wave, it can also generate a periodic sawtooth waveform or a ramp signal. Okay, so in such application, again, why do we use function generators? To test many systems, many circuits and systems. Sometimes we will need to test its functionality by applying different inputs to it. Okay, so those different inputs can be generated using a function generator. So one application where we need the sine wave to square wave converter is function generator. The other more common application is encountered in integrated circuits. So generally, you have a printed circuit board with copper connectivity. I mean, with copper wires for connectivity. So, for example, let's assume you have a digital processor on a printed circuit board. Okay, and a clock signal to that processor is coming externally. So generally, the dimensions of these wires will be in the order of few centimeters. Now, even though let's assume you have some very good clock source which is going to generate pure square wave, the copper wire is going to act like a RC circuit which can be approximated as a low pass filter. Okay, which it is a low pass filter. Now, if you take a square wave signal, for example, I've discussed extensively how to find the Fourier transform of a square wave signal. You can go through that. A 50% duty cycle square wave signal will contain only odd harmonics of the fundamental frequency. Okay, a pure sine wave will just contain one tone at the fundamental frequency f0. Whereas a square wave with a fundamental frequency f0 will contain a range of harmonics ranging from the fundamental all the way till infinity. Now, if I pass this through a low pass filter, of course, all the higher harmonics are going to get rejected. So for example, let's assume this low pass filter can be approximated as a brick wall low pass filter shown here. So this is the frequency response of a brick wall low pass filter. I'm approximating this RC circuit's frequency response. It's a very crude and bad approximation, but for argument's sake, we're just going to use this approximation. If you pass a square wave signal through this low pass filter, let's assume your fundamental frequency falls within the cutoff frequency. This FC is the cutoff frequency here. After that, the gain is 0. The low pass filter doesn't pass any frequencies at all. Okay, so what happens is it will reject all these higher harmonics. You will be left with just one harmonic at the output of this copper wire or this RC circuit. The Fourier transform will contain only one harmonic at f0. So therefore, the output will be a sine wave. Again, this is an approximation. So if you feed a square pulse here, you will get a waveform which looks like this. I'm approximating it to a sine wave. So all I'm trying to say is that on a printed circuit board at very high frequencies, typically the waveforms that will be propagating on these copper wires can be approximated to sinusoidal waveforms. Now, once the sinusoidal waveform enters a chip, once it comes inside a chip, now inside the chip you will need, because it's a digital circuit, it operates on binary levels, so you'll have to convert it back to a clock signal or a square wave signal. So that's another application where the sine wave to square wave converters are often used. Okay, that's another application where it's often used. So now we'll look at how to actually build some very simple sine wave to square wave converters, and then we will look at the positive feedback circuits as well. So first, I'm going to just introduce, so far I haven't spoken about the actual or the non-ideal model of an operational amplifier. I'll just introduce them one by one as we move to analyze different circuits. So one thing we said about an ideal operational amplifier is that the gain of an ideal operational amplifier is infinity. So which means if I plot V naught versus Vi, so let's assume V naught, the gain is finite. So this is V naught, this is Vi here, the gain is finite. If the gain is finite, okay, if the gain is finite, you will have a finite slope. As you keep increasing the gain, the graph will look like this. What will happen when the gain becomes infinity? This will overlap, the graph will actually overlap with the y-axis. This will be your ideal operational amplifier's characteristic. But in practice, of course, the output voltage cannot go to infinity if we are limited by the supply voltages. Most practical operational amplifiers, at least the older versions, they used to use dual supplies. So there will be a positive supply called plus VSAT or VCC. So let's call it plus VCC, and there will be a negative supply minus VCC. So which means you cannot exceed VCC and you cannot go lower than minus VCC. So the output of the op-amp, on the other hand, typically it will go very close to VCC. So that's called upper saturation voltage. It's called the saturation voltage when we are going to call it VSAT. So this is the positive saturation voltage. Okay. And similarly, we can define a negative saturation voltage as well. So this is the maximum voltage that the output can go to. It will be very close to VCC, minus VCC, and this will also be very close to plus VCC. So since we have studied operational amplifiers, at least a very crude way, we have studied about how to realize differential amplifiers in your previous semester. So you would know that some voltage drop will be lost to keep some transistors in saturation. So this is that, roughly that. So the maximum and minimum voltages will be very close to the maximum and minimum supply voltages. So we are going to call them plus VSAT and minus VSAT. So then the operational amplifier transfer characteristics will look like this. So what I'm plotting here is VD, the differential input versus the output. Okay, VD here is V plus minus V minus. Even if you apply a slightly positive voltage, V plus is slightly greater than V minus, the output, because it's supposed to go to infinity, right? Because it's a positive input. If input is positive, for an ideal op amp, V naught is A times VD, A is infinity. So if VD is greater than 0, V naught will be plus infinity. If VD is negative, V naught will be minus infinity. But we said we are limited by VSAT and minus VSAT, so the graph will look something like this. Okay, so this is the transfer characteristics of an ideal operational amplifier with saturation. Okay, output and output saturation. Now we will use this characteristic itself, this ideal characteristics of an operational amplifier, and try to use this non-ideal characteristics of an operational amplifier and see how it can be converted to a sine wave to square wave converter. What do you need to do? You have a sine wave. From this, you will have to generate a square wave. All you need to do is you can take an operational amplifier, and at the positive input, you can apply your sine wave, and you can ground the negative input. So if your sine wave exceeds 0, so let's assume this is 0. If your input exceeds 0, what will be the output of this operational amplifier using this model? It will be plus VSAT. So the output will be plus VSAT. So the waveform is going to look something like this. Output will become plus VSAT. And when your input goes less than 0, it will be minus VSAT. So the graph is going to look like this. Okay, you will have plus VSAT or the output going to minus VSAT. So now I have converted a sine wave to a square wave, a perfect square wave. Okay, so this circuit is what we call a zero crossing detector, right? So whenever there is a zero crossing, your output transitions from a lower voltage to a higher voltage. And here also, whenever there is a transition or a zero crossing, the output changes from plus to minus. Okay, so that's one. Okay, yeah. So now we will look at so we'll see if there are any problems with this implementation. Okay, I can directly use an operational amplifier in open loop and it perfectly works. Now, the operational amplifier fundamentally operates, okay, on the principle that if your input is greater than 0, so I'm drawing, this is the sine wave and this is the 0 level. If the input is greater than 0, then the output will become plus V set. Most analog circuits come with noise. Okay, a noise, I haven't yet discussed any lecture how to characterize noise, but for the time being, a noise, I'll just very briefly for a minute, I'll discuss how to characterize noise. A noise is a random signal. So you don't know what is the exact value the noise will take at any given time, but you can tell the statistics. Okay, if you take if you study the values it's taking and then try to fit a probability density function, typically they tend out to be Gaussian in nature. Most noises, I mean, those are called white noises and Gaussian white noises. So you cannot precisely say, for example, if you have a sine wave, you can, if you know the value at origin, you can precisely say, if you know the frequency of the sine wave and the amplitude of the sine wave, you can precisely say what will be the value of the sinusoid at any given time. But with noise, it's called as a random signal. So this is called as a deterministic signal. You can't precisely define what value the noise will take at any given time. So therefore, there is a proper study of that, how to characterize such a signal. There is a proper study for that. Right now, we don't need to know all of that. All I'm trying to tell you is that noise, it can have any value, it can take any value randomly. Okay, and that when I since I use the word random to characterize it, generally we use a probability density function. Okay, so generally, normally it turns out to be a Gaussian function with a certain variance. So noise will have a probability density function whose shape will be a Gaussian function with a certain mean, generally zero mean and a finite variance. If you know the variance, then you can know what are the range of values this noise can take. Okay, you can only know the range, but you will not know what value it will take at any given time. Now, generally, I can model noise at the input of the operational amplifier. I'll talk in more detail when we discuss about noise, but right now, your operational amplifier has to make a decision whether your sinusoid has crossed the zero or not in the presence of noise. Now, because noise is a random signal, it can take any value. This is going to corrupt that decision process. Okay. Previously, there was no noise, so it was very simple, but now there is noise. Now, your noise, it's your op-amp is now going to compare your input signal with noise. Now, for example, let's say at this point, if your noise is lower than the input, what will happen at this point? What will happen to the output of the op-amp? See, your noise is lower than the input. So what will be the output of the op-amp? Plus V set, right? So if your noise is at, I mean, I'm modeling noise as a negative terminal, it is lower. So even though your input has not crossed, because noise has gone lower than not crossed zero, ideally transition should have taken place here. Your output will undergo a transition here. Again, your noise can be here at this point, your noise can be greater than the, because it's random, at this point, even before it is reaching zero, your noise can suddenly go higher than the input signal. So what will be your output value at this point then? Minus V set, right? Noise is higher, so negative terminal is at higher voltage. So your output will go to minus V set. And I can have this randomly, again at zero crossing, I might go higher here, again there might be noise here, and so on. So what will happen here is that around the zero crossing, you will end up having, ideally you are supposed to get just one rising edge here. But instead you will end up getting multiple rise and falls. Okay, so this is called false triggering. In the presence of noise, you will detect unwanted edges at the output. So this is the problem with this circuit. If I use an operational amplifier directly, just this application is called a comparator. I'm just comparing two voltages and telling you what is the output. See, output is binary, right? It's plus VSAT or minus VSAT. I'm just comparing two voltages and saying it's plus or minus. Now, that comparison process in the presence of noise is corrupted, and you will end up producing unwanted edges or unwanted highs and lows, especially in the region where the decision is being made. See, the thing is that you will not have that problem here because the signal level is already much higher. See, noise is some random signal like this. Okay, if your signal level is already much higher, even though there is noise, op amp has sufficient margin to make a right decision. Is that fine? So even though there is noise, at this point I'm not seeing, I've drawn a clean waveform here. That's because even though there is noise, the signal voltage level is much higher than the noise level. So we are fine. The problem happens at the decision making process. At this edge, the problem occurs. Okay, so this phenomenon is called false triggering. And again, for example, most digital systems operate on edges, rising edges or falling edges. Now you end up giving unwanted edges to the digital system, and it might even fail. So this is the problem. This is a genuine, a practical problem with using an operational amplifier in open loop as a sine wave to square wave converter. Now, I'll just ask you a few more questions. Do you think that problem will be resolved if, let's say, instead of using a zero crossing detector, I just need a square wave. Let's say for the time being, I don't care about duty cycle also. I don't need to compare it at zero. Can I compare it at some other level? So I'm going to feed. So this, I'm going to call it as Vref, and this here is Vi. I'm going to compare it at some other level Vref. Now, when your input exceeds Vref, then at this point you will get a rising edge, and at this point you'll get a falling edge, and so on. Again, the rising edge will come much later. Of course, duty cycle won't be 50%, but you'll get a waveform that looks like this. Do you think this is resolving the problem? Remember, there is noise present still. I mean, there is still noise here. Even on top of Vref, there will be noise. Is it resolving that problem of false triggering? Yes, noise is intrinsic to op amp. Yes. It's not solving it, right? You have just shifted that problem to some other point. That's it. You have actually shifted it to some other point. Okay. So it's even there is a problem of this detection. Detection in the presence of noise becomes a problem. You will end up creating false triggering. You'll produce unwanted edges at the output. Now let me pose a simpler question. Does that false triggering depend upon the slope of the sine wave, frequency of the sine wave? For example, let's assume I have a sine wave, both sine waves are of same amplitude, but the frequencies are different. One sine wave has a lower frequency, another sine wave, let's assume it's twice the frequency, it's much faster, or it's much higher. It's like this. In which one do you think the triggering problem will be worse? Let's assume the op amp is same, noise is same. In which one do you think the triggering problem will be worse? So look at this sine wave here. The noise signal can corrupt as long as your input signal is within a certain range. Okay, as long as your input signal is within, see, this is the voltage range. So right, once you exceed a certain range, then your input signal level will be much greater than noise. Then you don't have to worry about it. A high frequency signal will spend much smaller time before it exceeds that threshold level. So you get what I mean? A low frequency signal will slowly transition from this range. I mean, this region, let's assume this is the region where your input signal level is comparable to noise levels. Okay, so if you see a high frequency signal, so let me probably draw it on a different page. So look at it this way. This is the high frequency signal, a low frequency signal. And I am interested in the voltage levels here. So this is the voltage level at this point, and at this point, until this region, noise can corrupt it. Now look at the high frequency signal. That's going to cross much faster. So it's going to do this. So to cross the threshold level, this is the region in which noise can affect its decisions. Now tell me, looking at these two waveforms, which one will have more false triggering? So this is the low frequency and this is the high frequency one. Which one will have more false triggering? The low frequency one, the lower, right, because it's spending longer time traversing this region, right? So as noise is corrupting here, it has longer time to produce unnecessary edges. Okay, so yeah. See, the question is, the one of you are asking, the high frequency signal has more zero crossings. That is true, but we have to look at per cycle how many unwanted zero crossings are you getting. Okay, per cycle, how many unwanted zero crossings you are getting. So per cycle, this will be more. Okay, this is of course going to spend longer time. So lower the frequency, the more will be your false triggering. Okay, in any given one cycle, it will be lower. That's what I'm trying to comment. Yeah. Okay, so generally for higher frequency, so that's why if when I showed you the sine wave signal like this, what I was trying to tell you is that if you choose 0 as the threshold point, then sinusoidal signal has the maximum slope at origin. If I choose this as the threshold point, some other point away from the origin, the slope here, let's call it S2, and the slope here is S1. Obviously, S1 is going to be greater than S2. S1 is going to be greater than S2. So which threshold point will you choose for comparison? Will you choose this Vref or 0? Which one will you choose? Remember here the slope is less, S2 is less. So if you want to have less false triggering, which one will you choose? 0 as, because the slope is higher at that region. Okay, you will choose 0 because slope is higher, you will have fewer false triggers. That's it. So that's what I was trying to explain here through this. The frequency is the same, but the slope here is lower in comparison with this. But whatever it is, we have not eliminated the problem of false triggering. Now the question is, can we eliminate this problem of false triggering completely? That circuit which actually eliminates this is what we call a Schmitt trigger. It's a sine wave to square wave converter, but it will not come with the problem of this false triggering. Okay, so now why does false triggering occur? You have to look at the characteristics of your zero crossing detector circuit. The characteristics look something like this. If your input signal is greater than 0, it becomes plus VSAT. If your input signal is less than 0, the output is minus VSAT. Okay, I may not have drawn it symmetrically, but you get the picture. So if your input signal increases, then your output becomes minus plus VSAT. I mean, if the direction in which it flows is this way, output changes is this way. And similarly, as you reduce your input, the moment it goes less than 0, it traverses in this direction. Okay, so as you increase your input, this is the path. As you decrease your input, the path is the same. The problem of this false triggering is happening because of the same path for both directions in which the input is traversing. I mean, the path the output traverses is same. Okay, so one way to fix this, theoretically, one way to fix it is that, let's say, if you increase your input, let's say at this point your output has changed. At one point you have changed your output, so output has become plus VSAT. Now, when you are in this point, where that's after the transition has taken place, you don't want to trace the same path back, because if you do that, your output will become minus VSAT. Instead, you suddenly change the threshold point itself. After the transition has taken place, you change the threshold point itself. If you do that, then the output will stay where it is. Is what we are trying to achieve? The problem that's occurring here is that in this region, if your input goes less than 0, after, let's assume your input has gone greater than 0 once, you have come to plus VSAT. Now at this point, your input is going less than 0, because in the input and noise together, it's giving a negative differential input. So suddenly your output is going to minus VSAT. But what if the moment your output changes, I will somehow change the threshold point itself. I will no longer keep it at 0. I'll keep it at, say, some negative value. Instantly, let's say I'm able to do that. Then, even if your input is negative, your output will still be plus VSAT. Only when your output reaches a certain negative value, then you change it. Okay, so this is called hysteresis, transfer characteristics with hysteresis. Again, this word is borrowed from theory of magnetism. The word was also coined in late 1800s, 1890s is when the term was coined. We see a similar hysteresis phenomenon in theory of magnetism, where the graph, I mean, it doesn't have, if you increase a certain quantity, okay, then when you reduce it, the path it traces will not be the same graph. It will be slightly different. Okay, either you can say there is some delay, but hysteresis graph looks like this. Okay, if you increase your input in one direction, the graph will be changing in a certain manner, and as you reduce your input, it will change in a different direction. So there is hysteresis. It will not take the same path as you took when we are increasing the input. So if you can build hysteresis, then we can solve this problem of false triggering. So we'll look at two different ways of building hysteresis, and we will look at two different configurations of Schmitt trigger using an operational amplifier. So now look here, in the circuit I have shown here, I have applied the input at the negative terminal, and if you see here, the resistive feedback is at the positive terminal. So of course it's clearly a positively fed back system. It's a positively fed back system. Now we'll try to draw the transfer characteristics for the circuit. Okay, now look at this. Your output, if your input V plus here is simply V naught into R1 by R1 plus R2, and V minus is Vi. Now let's assume your output V naught is Vsat. Let's assume that it is at plus Vsat. Okay, so which means this node will be at R1 by R1 plus R2 into Vsat. So I'll call this as beta. This factor is less than 1, so this will be beta times Vsat. Output is at Vsat. Now at what will be the point, what will be the voltage, input voltage at which the output will change to minus Vsat? See, you applied the input at the negative terminal. So if the negative voltage exceeds the positive voltage, then the output will become minus Vsat. So what will be that value? So let's call this minus beta Vsat. Your plus V plus is at plus beta Vsat, and V minus is at Vi. So if your Vi is greater than beta Vsat, if your Vi input is greater than beta Vsat, what will be your output? Output will be minus Vsat. So that's what I've shown in this graph. If your input, so this is your input signal, so let's probably draw it for fresh. If your input signal, initially we have assumed your input output to be at plus Vsat. Now my input has changed, has become greater than beta Vsat. And we just saw from the analysis that when you exceed this, your output goes to minus Vsat. Now what will happen as I increase my input? Let's assume if I increase my input greater than beta Vsat, further I keep on increasing it, what will happen to the output? See, now what is the value of V plus now? Now the output is at minus Vsat, V naught is at minus Vsat, and your V plus will be at minus beta Vsat, and V minus is at Vi. Now I'm making input more positive. If I make Vi more positive, the negative terminal will always be higher than the positive terminal. So which means what will be the output voltage? It will always be minus Vsat. So this is how the graph looks like. It will remain at minus Vsat. Now what I'll do is that I'll keep reducing my input. I'll keep reducing. Let's say I've increased it all the way till infinity, and I'm now reducing it. I'm now reducing it to this point. Will the transition take place at plus beta Vsat? So look at V plus now. V plus is at minus beta Vsat. The transition will not take place at plus beta Vsat because now your V plus is at minus beta Vsat, and your input signal is reducing further. Now it comes back all the way to minus beta Vsat. it comes all the way to minus beta Vsat. At this point, your V plus is staying at minus beta Vsat, but V minus is now going lower than minus beta Vsat. So V minus is now, for the first time, it's going lower than the V plus. So V plus is at minus beta Vsat, it's going, Vi is going less than minus beta Vsat. So at this point, the transition will take place. So what will be the output now? V minus is less than V plus. So your V naught will be plus Vsat, right? V plus is more, so it will be plus Vsat. So your output goes to plus Vsat. And after that, it will stay there, right? If you keep reducing your input further, your V plus has now become equal to beta plus beta Vsat. So now look at this. The moment transition has happened, the threshold level has instantly changed. The threshold level changed instantly. Okay, previously, just before the transition, the threshold level was minus beta Vsat. The moment the transition happened, you changed the threshold level to plus beta Vsat. So therefore, even if you slightly reduce this input, you will still stay at plus Vsat. Okay, so if you reduce your input further, Vi further, it's going to be obviously lower than V plus. V plus is at plus beta Vsat, which is a very high positive voltage, so it's going to be lower. So, and you're now start to, let's say you start to reduce Vi, the transition will not take place at minus beta Vsat, but rather it will go all the way to plus beta Vsat, and then the transition will take place. So this is how the graph looks like. Okay, so the graph looks this way. So as you increase, let's assume that you're increasing your input from minus infinity, it will traverse this path to this part. When it goes from minus infinity to plus infinity, this is the path it will traverse, what I've shown here. Then you reduce it from plus infinity to minus infinity, the path it will take will be something like this. This is the path it will take. The paths are not same on either directions. So we have now built a hysteresis into this op amp. So what will happen is that if you feed a sine wave, when your sine wave crosses plus beta Vsat, you're going to get a rising edge. Okay, so this is say plus beta Vsat, and this is minus beta Vsat. And when your input goes lower than minus beta Vsat, you will get a falling edge, and so on. So at this point, again, it will raise and it will go lower. Okay, so that's the trajectory, or rather the this is the transfer characteristics of this circuit called Schmitt trigger, and this is how the waveform will look like. Because if your input exceeds plus Vsat, output should be minus Vsat. So what you will be getting here is that you will get minus Vsat, it will remain constant, it will go to plus Vsat, remain constant, and then minus Vsat, and so on. Okay, so can you tell me what will be the duty cycle of this output? What will be the duty cycle of the output in the Schmitt trigger circuit? The transition, remember, it takes place at this point, plus beta Vsat. It's a symmetric transition, plus and minus. In the negative cycle, it takes place at the same point. Yeah, right. The on duration will be this. So at this point, from this point to this point is your on duration, and your off duration again is this. Okay, so is the on and off duration same? Yes, so you see that it is 50%. Yeah, that's it. We will now look at another way of course, we are using positive feedback. So this is what we have shown here. This is an inverting Schmitt trigger. If you see, for positive values of input, you're getting negative output. So it's an inverting Schmitt trigger. Now I'll apply the input terminal to the positive terminal itself. So there is positive feedback here. Now to this circuit, we will try to draw in the same way. We'll try to analyze the circuit and draw its transfer characteristics. So let's start from, see, now I'm applying a positive input. If your input is positive, it is directly connected to a plus terminal. So I can expect V naught to be plus Vsat. I'm just giving you a very high positive value. I applied a very high positive value. So output is at plus Vsat. Now V minus is at 0. V minus is always at 0. Your V plus will be superposition of two voltages. One Vi, the other one V naught. So I can probably write V plus as superposition of two voltages. So you can assume V naught is 0 and find its voltage. So that will be R2 by R1 plus R2 into Vi plus R1 by R1 plus R2 into V naught. So this will be your V plus. So if this voltage is greater than 0, your output will be plus Vsat. V naught will be plus Vsat. If this term is less than 0, then your output will be minus Vsat. Now let's look at it. I have told you one thing, that if Vi is positive, a large positive value, then we said, okay, since it's connected to the positive terminal, then output may also be close to VDD. I mean, it's plus Vsat. So let's start with that condition. So this is plus Vsat. Okay, so this is at plus Vsat. Now I'll equate it to a condition. What I'm doing right now is that your output is positive, and I'm now slowly trying to find a condition when it will trip, when the output will go from plus Vsat to minus Vsat. So of course input has to reduce, because if your positive terminal reduces, then you can think the output will go to a negative voltage. So I'm now reducing my input. The condition that I need to satisfy should be this voltage, V plus should be less than 0. Then the output will be minus Vsat. So if you equate this, you will end up getting Vi. You take this term to the other side, you will end up getting Vi less than R1 by R2 minus of R1 by R2 into Vsat. So I'm going to call this term as beta. So this will be beta here is the ratio of two resistance R1 by R2. So it will be minus of beta times Vsat. So if your input goes less than minus beta Vsat, then your output will go to minus Vsat. So this is the graph. So I've started from here. Remember, we have started from a very large negative voltage and positive voltage, and we are traversing this way. And at this point, the transition has taken place, and we are moving in this direction. After this, if you keep making your input negative, output will stay put at minus Vsat. Okay, so the output will stay put at minus Vsat. The moment output goes to minus Vsat, what will happen to this equation now? See what's happening here. Whenever you introduce a hysteresis, the threshold point changes immediately. It becomes minus Vsat. This equation becomes minus Vsat here. So now for the output to change its sign, this voltage should become greater than 0. Okay, so if you equate that condition, the point where the transition takes place is Vi greater than plus beta Vsat. If your input is greater than plus beta Vsat, at that point your output will go to plus Vsat. So on the other side, I'm reducing my input. Transition doesn't take place beta Vsat plus Vsat. So this is how the graph looks like. So on one side, it traverses in this direction. On the other side, it traverses. When I say other side, I'm talking about input changing from plus to minus, plus infinity to minus infinity. The directions are different. The trajectories are different on the transfer characteristic. Okay, so by doing this, we have built hysteresis. By building hysteresis, we can avoid the problem of false triggering. So now some very quick questions based on these characters. So let's say I apply an input. I'm going to apply an input to a op-amp based Schmitt trigger. Let's say Vi, mod of Vi. So the sine wave which you are applying, it turns out it's smaller than beta Vsat. Mod of Vi is smaller than beta Vsat. What do you think will be the output? So look at both the transfer characteristics. I'll just quickly draw the transfer characteristics. For one guy, the transfer characteristic looks something like this. So this is your inverting Schmitt trigger. Okay, so I'm sorry. For one guy, the characteristic looked something like this. Okay, so the graph looks something like this. Now I'm saying that this is minus beta vsat, this is plus beta vsat. For other guy it was slightly different. I'm applying a sine wave. Look at this, I'm applying a sine wave whose value is less than plus minus beta vsat. The threshold points are here. So what do you think will be the output? Yes. So you cannot exactly say, because if you see in this region, when your input is between minus beta vsat and plus beta vsat, there are two possible states. It can either be plus vsat or it can be minus vsat. And that depends upon the initial condition or the previous state. What was it before? Okay. So therefore, if your input should be greater for your Schmitt trigger to switch. So if you apply a pure sine wave to a Schmitt trigger, your output will be either saturated at plus Vsat or it will be minus Vsat if the amplitude of the sine wave is less than mod of beta Vsat. Okay, if your amplitude of this sine wave is less than this, it will either be at plus Vsat or at minus Vsat. So if I ask you what is the average value, if your input is between minus and plus beta Vsat, what will be the average value? Let's say absolute value of the average value. Right? If let's assume that your input is less than minus beta Vsat, the average value can either be plus Vsat or minus Vsat. So if you have a signal whose value is a constant, the average value is the constant value itself. Right? So that's the constant value itself, and it will be either plus Vsat or minus Vsat. And I'm asking you the absolute value of the average value. Absolute is remove the sign, it will be plus Vsat itself. So for your Schmitt trigger to actually change its polarity, you need to apply an input which will make it exercise, which will make it cross the threshold points. That's one very important criterion. So if you apply an input smaller than this, I mean, this is an experiment I often observe in lab. So sometimes students, they apply very small amplitude sine waves and you don't see the triggering happening. I mean, you don't see any outputs at all. It will be stuck at either plus or minus Vsat. So that's why you should apply an input greater than this. Only then you will see a perfect, transitions taking place at the output. Okay. So for your sine wave to square wave converter, this beta times Vsat, the amplitude of your sine wave should be greater than this. Only then you will get a perfect square wave at the output. Okay. So that's it. Very briefly, we discussed what is a Schmitt trigger. And we also discussed, in fact, we spoke about sine wave to square wave converters. Without, probably you guys at this point don't have an understanding of noise, but still we try to understand how we can have false triggering, how an op amp when used as a comparator, as a direct comparator, it can end up giving unwanted rising edges, and how that problem is resolved when we go to a Schmitt trigger. Okay, of course, there are some problems with this circuit as well. We haven't discussed the practical implementations of the circuit. But the word Schmitt trigger is often used for other circuits. I mean, I'll talk about it in some other lecture. There are some simple MOS-based implementations for Schmitt triggers as well. We'll talk about that at a later lectures when we discuss in an advanced circuit design course. But at this point, using operational amplifiers, they can serve as very good Schmitt triggers for lower frequencies, and provided you should meet certain conditions. The amplitude should be greater than plus beta Vsat, and you will get a 50% duty cycle if your positive and negative voltage levels are the same. Okay, so that's it. We'll discuss more about the applications of op amps in the upcoming lectures.